Hey, howdy everyone. I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin, and this will be a lecture on ridge regression. This is carrying on as within my machine learning courses, we've started to get into methodologies for prediction. We've already covered a bunch of methods on inference, and we'll go ahead and we've just started with a previous lecture on linear regression. Now we'll go ahead and get into ridge regression. Now, what's our motivation? Why do we want to cover this topic? Well, specifically, still very simple and interpretable, and when we're just getting started in machine learning, it makes a lot of sense to start with the simple and the more interpretable. Don't worry, we'll be building up to random forest and neural nets later on. Also, we want to get at this whole idea of the variance bias trade-off and provide you with a really nice kind of a application of that and demonstration. And this is an opportunity to introduce our first hyperparameter for the purpose of prediction. And so that's going to be very useful too. So let's cover ridge regression. Let's get into it. Now, in order to get into ridge regression, let's do a really quick recall on just general linear regression. And so the idea of linear regression, it's a parametric model. It's got very simple parameters. We are doing a linear weighting with our B parameters, or slope parameters, for each one of the predictor features, and we will add in a intercept term to that. Now, this way we can move from this is our function to go from the predictor features, alpha equals 1 through m predictors, to a response feature, and we're just assuming one single response feature here. And so our parameters we can tune are going to be all our B1s through Bm and our intercept. We will solve for these parameters or train the model parameters in the presence of our data, going from I equals 1 through n data that are available to us by using the L2 norm. That'll be how we take each of the individual errors across all of our data and summarize it into a single number. That's the whole point of a norm, is to go from a vector to a single measure that must be between 0 to infinity, and we'll use that as a summarization of our error. We can minimize that, and we've talked in the last lecture about the issue, a couple lectures ago, about the issues about choosing a norm, general P norms versus working specifically L1, L2 norms. So we'll work with an L2 norm when we do traditional linear regression. Well, let me make some general comments about linear regression. Linear regression model may be still too sensitive to the training data. For sparse or very high variance data sets, we may find that even though it's a very simple model, and we talked about the idea that more complicated models tend to have greater model variance, we may still find this model variance too high. And so for single training data, there's only one possible linear regression model. In fact, we can expect that when we go ahead and build a model of linear regression, we don't have any dials to turn. We're just going to get one single set of possible parameters that we can train for a given data set. So this is interesting. We want to, while this is a good fit under the constraint of the linear parametric model and least squares optimization, it's the very best estimates. It does minimize the L2 norm. Still, we may consider this not to be suitable because of the issue around high model variance. So what are we going to do? Well, let's just recall the idea of the variance bias trade-off. And so how does this work? We are going to, in the purpose of prediction, we're going to estimate a function f hat, which is going to provide us with the very best estimates of y hat, which is our response feature. Once again, we're focused on the most accurate estimates. When we're doing predictive statistics, we're trying to predict the next possible outcome from a system, from a population. A great way to think about it from the book Savai in 1996 on a Bayesian tutorial, the first chapter, they talk about this idea of given an assumption of the population. In case of coin tosses, if you assume the coin is fair, if you're going to flip the coin 10 times, what's the probability of a certain outcome, heads or tails? In this case, it could be 7 heads. What's the probability of that? That's prediction, trying to predict the next result from the population or from knowing about the system. Now, we assess accuracy in the model, once again, we're calling this, is by using some type of measure of quality of fit, because we need to make a selection of the best method to use. There's not one single model that will be the best for all possible data sets. Now, we're also going to include experience and understanding the data and so forth, and knowing about the limitations of each of the methods. That's why it's important to understand what's going on under the hood and why we cover theory and not just dive into methods. How do we measure the quality of fit? Well, we're going to be working with the mean squared error, and that's typically been the measure that we are optimizing, as we did with the linear regression model just now. And when we're judging the model for the purpose of training, we'll work with mean squared error. Now, that's fine and dandy to look at that when it comes to training, but at the end of the day, what's really important to us is not how the model performs at the training data, but how it performs in testing. And we show this as with the not symbol, indicating the next location we want to make a prediction. I want to know how I perform in expectation for the true value at that location minus or the delta with my model prediction, my very best estimate of the model, and the predictor features which are available at that testing location. I need to know how my model performs in the case of testing. And so I'm concerned about the expected test mean squared error. Now, it's really great. You go to the book of James and al., and they expand out this expectation. It's a quadratic, we can expand it, and we get 3 separate components of error, and fortunately, error related to variances are additive, and so we're able to add them together really nicely. And so once again, we have 3 components: model variance, model bias, and irreducible error. Now, recall model variance is the variance due to the fact that our model may change if the training data changes. In other words, this is the component of sensitivity to the training data. If we change the training data a little bit, do we have huge model variance? The model will switch dramatically. Or will we have a model that will be more stable in the face of changing the training data? Model bias is error due to using an approximate model. The model is just too simple. If we're trying to fit a phenomenon with a linear regression model, but it behaves very non-linear, it's got really complicated features in it, we're going to have high model bias. Our model's just not flexible enough to fit the true phenomenon. And irreducible error, this is the component that we can't get rid of. It is due to the fact that we haven't sampled all of the features that matter. We haven't sampled all the ranges and combinations of the features. And so it's just limitation of our data set. Now, we got model parameters that we want to work with. And so the definition of model parameters, once again, are the parameters that we can set to fit the training data. So for example, if we have a third order polynomial as shown right here, we have the B3 through B1 plus, we could call this B0 or C, which would be the intercept term. These 4 parameters are the parameters we can change, and by changing them, the model can shift up and down. It can change the shape and form. We could even make it change it so it is actually curved downwards or upwards, and so forth. So we have a lot of degrees of flexibility with this. But the hyperparameters are in fact different than this. The hyperparameters, in fact, they control the complexity of the model. They control the sensitivity of the model to the data. And so in this case of a polynomial, the hyperparameter would be, do we use a first order polynomial, which would be a line, third order, fifth order, seventh order polynomial. And you can see immediately, if we're only concerned about fitting the training data, we would always be driven towards the most complicated model, the most flexible model, because that would minimize error at the training data. But it would not result in the best model away from the training data. Consider if we had training data, actual testing data that was consistent with this training data, and we had point here, here, and here, and so forth, we would expect this model, in fact, would be quite inaccurate at the testing data locations. Or if we had another additional observation, of course, that we're trying to predict in the future, this model would not be very robust. Can you imagine? We had a new location here, a permeability was needed at a depth between 40, and 60, this would probably not be the very best estimate to minimize the error. And so we're going to use a training and test workflow. We'll separate the data into training and testing data. We will train our parameters to maximize accuracy with the training data for a set level of complexity, for a set hyperparameter. Now what we can do is we then tune the model, and effectively in many methodologies what this is create many models of a range of hyperparameters and select the one that has optimizes complexity. In the case of decision trees, this works very well because the complicated tree, a subset of it, is a simple tree, and so we can prune backwards. And when we cover decision trees, you'll see that it's very natural to have a dial. The dial could be just simply the number of levels, or more often the number of leaves on a decision tree or regions. And we can go ahead and just tune that back and get from a complicated to a simple model by doing that. Very useful. Okay, let's get back into ridge regression. I thought that was important to do a really quick recall on some fundamental concepts of parameters and hyperparameters, because this is going to be very important when we talk about ridge regression. Okay, so what we're going to do is we're going to perform regular linear regression. We're using the L2 norm still. So you'll notice if we go back here, we're going to minimize the sum of the errors at each of the training data locations, and you'll recognize immediately that this is simply our linear regression model estimator right here. This could be represented as y star I or y hat I, basically the estimate at the data location. The training data value is right here. So this is just the squared error that we want to minimize, and we're summing over that. So this is the residual sum of squares. But what we'll do is we'll go ahead and add another term. And this term is very interesting. Remember, we're trying to minimize everything in the brackets. So we want to minimize not only the error at the training data, the square of the error at the training data, we also want to minimize, which is interesting, the sum of the squares of the coefficients. This is called a shrinkage penalty. Now we want to dial, we don't want to just put sum of squares here. We want to have some control over what's the influence or weight of this component that we're minimizing, and that's lambda. This is our coefficient that allows us to control to what degree is minimizing the square of all of our coefficients important or not. Now this is fascinating. We're putting a value on a simpler model from the standpoint of coefficients that are close to zero as possible, or small as possible is what I should say. Okay, so let's go ahead and we'll think this through. Like, how do we go ahead and solve for these coefficients under this additional constraint with the shrinkage penalty? Now what's very cool, because the fact that we are working with an L2 norm, we still retain the ability to solve this problem with a closed form solution. We can solve for the entire vector of coefficients for a ridge regression model under the constraint of a lambda and minimizing the square difference of or error at the training data locations and the square of the coefficients themselves, trying to minimize them down too. So what we're going to minimize, the best way to solve this is to go ahead and start working in matrix notation. This makes it much simpler and easier to understand. And so what we'll do is our RSS, residual sum of squares, can be expressed. Basically, we're just taking this right here and expressing it in matrix notation. This is not too hard at all. In fact, what we recognize immediately is that the y is just simply a vector with all of the response feature values over data samples I equals 1 through n. The x will be a two-dimensional array with, for every one of our samples, we will have each one of the subsamples I equals 1 through n, and all of our predictor features alpha equals 1 through m. We will have all of our training data. This is effectively all of our response features that are being fed in for each one of the samples. And lambda is going to be our shrinkage factor. And once again, beta is going to be a vector with all of our coefficients that we're trying to fit. So this is the same as that in matrix notation. And so what we can do is we can just take a look at that. Once again, I've just labeled the individual components, the residual sum of squares, and at the error at the training data locations and the shrinkage penalty in the shrinkage component on the other side. Now we can expand the RSS component of it. And if we do that, it's quite straightforward. We'll end up with these three components right here, and we retain the shrinkage penalty component right here. Now in that form, it's very straightforward to do the partial derivative with respect to the beta vector. In other words, we're trying to use the usual optimization, partial derivative, and then set that equal to 0 so we can find the very best beta coefficients. If we take this, what we'll find is for the first one, y transpose y, this will just disappear because of the partial derivative. This other component right here, the x transpose y, to negative of that, we retain that, but we lose the beta. We have a beta transpose beta, so we'll retain a single beta here. Beta transpose beta, we retain a single beta transpose here, and we get a 2 as a coefficient on each side. This is a really nice form for us to now solve. We can do a little bit of minor alteration, algebraic type matrix algebraic alteration of this matrix equation. And the result is we can put the negative 2x transpose y on the other side. It becomes positive. We can go ahead and drop all of the 2's. And then we can go ahead and group the betas. And this is nice in matrix notation. If we want to do that, since the lambda is a constant, all we have to do is represent it as a lambda multiplied by the identity, which is simply going to be a matrix, which would just be 1s on the diagonal, 0s otherwise. And we get this relationship right here. Well, to solve for the betas, we just have to take the inverse of this, multiply it by the right-hand side. And what we'll note is that in general, we'll expect this component right here to be invertible, so we'll be able to solve for the beta coefficients. So we've just shown how we have a closed form solution in matrix notation for ridge regression beta or B parameters that we're going to use in our model. So let's just give some thought to what we're actually doing to our model. While we're applying the lambda coefficient, how are we adjusting or altering the model? And so what we're doing while regularizing or shrinking the coefficients, the B alphas 1 through m towards 0, we're in fact introducing a bias to the model. We're making a sacrifice. In fact, what we'll find is that there is actually going to now be a difference between our estimated function and the actual system. We are sacrificing accuracy of our model. How do we visualize that? Well, let's go back to a very simple one predictor feature, one response feature. And if we looked at the training data set right here, and if we applied linear regression such that all we were concerned about was minimizing the error with regard to the training data, then we would get this blue line right here. That would be linear regression. But what happens with ridge regression is we put a penalty term on the size of the slope. In other words, we're trying to shallow the slopes a little bit. We're shallowing the slopes a bit. Now, of course, this is going to introduce a bias because we're no longer minimizing the sum of squares at the training data locations. And so we're going to have a bias in our model now, and you can see it right now. This ridge regression model right here would result in a systematic bias over the range of possible predictor feature values. So we're going to have bias as we increase the lambda coefficient, but at the same time, what we're going to do is we're going to gain in a reduction in model variance. We're increasing model bias, but we're decreasing model variance. The sensitivity to the model, to the data, is going to decrease. The shrinkage will reduce model sensitivity, and the result is we might actually have a better model because it's more robust, even though you can see we have added model bias. Now, let's just think it through. What would be the impact of these lambda coefficients on the model? So I always like to take the extreme cases to really understand what's going on. It's quite trivial to recognize that if we set lambda equal to 0, the solution at lambda 0 is the same as linear regression, and it'll approach linear regression as we approach 0 with a lambda. Now, as lambda goes to infinity, this is pretty interesting. what'll happen here is that we are shrinking all of the model coefficients, the B alphas, to a very small value. They're all approaching 0. And so as lambda goes to infinity, what actually happens is this term cancels out, this term cancels out, and the result is we have minimization of the sum of the squares between all the training data with the intercept term only. We've lost all of the slope coefficients. And so what would be the very best intercept? Basically, if we're going to make a horizontal line with no slope, what is the very best estimate of that parameter such that we minimize the square distance? And we know just automatically that in the case of an L2 norm, it is the mean or the expectation that in fact will minimize. So we would want to build a model as the lambda goes to infinity that would simply be the average of the response feature. All right, so that's it. That's the extreme cases. So now we go back to it as we're tuning the hyperparameter lambda. We in fact are going to be observing a model variance versus model bias trade-off. And we can find an optimum lambda parameter from the perspective of minimizing our total or expected test error. Now, what does it look like? Well, I put together a very simple set of examples. And so we have this previous density versus porosity relationship. If we put the lambda at 0, we will simply get linear regression, and this is the same as a linear regression model. Lambda at 1, 2, 3, 4, and 5. What you're seeing is, do you notice it? The slope is starting to decrease. We're starting to see the slope term going towards 0. Now, just to show it, just to prove it, I went ahead and I set lambda very large and I reran the same program using just scikit-learn. And what happened was we in fact did get a model that is estimating simply as the average or the mean of the response feature 12.2% over the entire range of possible densities. So that works. That works. Let's give ourselves some training and testing data. We have the training data in gray and the testing data is in red. It's a pretty fair train test mix. We're not extrapolating with the test data. You might argue that in some cases we have training data right on top or close to it. Random selection will do that. We could be a little bit more designed with it. We go ahead and we run the model such that we are changing the lambda parameter. And let's observe the variance explained. That's a pretty good measure of the performance of our model. And what we see overall is that we got the best performance in variance explained with lambda equal to 0, in other words, linear regression. And then we were seeing a steady decrease in training and in testing with regard to variance explained. Now, of course, I should comment if we want to do a really good testing and tuning of our hyperparameters, we really should do a full k-fold cross-validation. So we've only done here more of a cross-validation, a jackknife type approach where we left some data out for testing. But it wouldn't be a bad idea to do that. Now, if we look at the mean squared error of the model, another good indicator, we'll see the performance in testing and the performance in training over multiple lambda values. And we'll see in general that our model is getting worse as far as accuracy. So this is an interesting circumstance. Let's try to take a look at the other side and look at model stability. Let's see if we in fact are getting more stable model. And so what I did was I looked at the variance of the slope coefficient over multiple bootstrap resamples from the data. So I bootstrapped the data, got multiple bootstrap realizations of training data, and just kept track of the variance slope for different lambda parameters. And this is the result I got. What can we see? In general, we are getting a more stable model as we increase the lambda parameter. So we are seeing more model stability. Now, what's going on here with this result right here? Well, first of all, recall it's not appropriate to tune the hyperparameter with the training data. This would always drive us to a very low lambda value, and we'd always be overfit. Must tune the lambda parameter with the testing data, and we did more of a cross-validation type approach, just withholding some testing data. But we could have done a full k-fold cross-validation. Now, in this example, was the best model. And if we were to tune the hyperparameter lambda, we would have selected 0 as being our hyperparameter and just used linear regression. Now, one comment I'll make is that probably has a lot to do if it was a very simple one predictor, one response feature. We had a very nice clean relationship. We had quite a bit of training data available to us. And so overall, with this simple circumstance, model variance was not a major factor for us. And so the result was that we did not benefit from the shrinkage parameter being applied to improve model variance. So that was a discussion of ridge regression. I do have a workflow on GitHub for applying ridge regression, just like I have for all of the machine learning methodologies that are discussed here. That's at my GitHub account, GeostatsGuy on GitHub. That's my account. You'll see there's a Python numerical demos repository with a lot of workflows that are available to you. All right, I hope this discussion of ridge regression was useful for you. I am, once again, Michael Pyrcz. I'm an associate professor at the University of Texas at Austin. I teach and conduct research in data analytics, geostatistics, and machine learning. This is all part of a brand new course on subsurface machine learning that I've been teaching this term, and I record every single one of my lectures to share with my students so they have a resource outside of the class to review, and even after they finish up with the class, and for working professionals and anyone else interested from the public in learning more about this topic. All right, if you want to see more of my content, check out my YouTube channel, GeostatsGuy Lectures, my GitHub account, GeostatsGuy, my Twitter account, GeostatsGuy. So I hope this was helpful to you. Hey, everyone, take care. Okay, bye.